Bismillahirrahmanirrahim. On the demand of Rizki from Sumatra, Indonesia. This is a problem of complex analysis and theorem is MORERA Theorem. Uh, its statement is if fz be continuous in a simple connected domain D and integral of fz dz line integration along uh, gamma curve is equal to 0, where gamma is a rectifiable closed Jordan curve in D, then fz is analytic in D. If any curve fz is differentiable at every point of domain D, then we can say fz is analytic in D. So we have to prove fz is differentiable at every point of domain D um, for this. First, this statement we use to prove that this integral in domain along any curve is independent of curve. But it is only depend of initial point and final point for this function fz, which is which have property given here. Fz is continuous in a simply connected domain D. So this portion I also said that this portion is we use to prove the uh, integral is independent of um, curve, but it's only depend on the points initial point and final point, and rest as fz is continuous, we use to prove our required result. Fz is analytic. So we start our theorem step by step. If any problem, you can ask me by YouTube channel or other link. So we draw first a domain D, which is defined here as a simply connected domain. So we define any simply connected domain D, and for proof by use of this, first point in curve integral is differentiable. So integral is integral is independent of curve. So first we curve this closed curve gamma. Gamma curve is composed of two curve, gamma 1 and gamma 2. Here we gamma gamma 2 gamma 2 is direction from point z0 to z1. Here z0 and z1 is arbitrary points, means this point lie in domain, everywhere in domain, but here is a a fixed point. For gamma 1 we start z1 and go along this curve gamma 1 to z1 point. Also gamma 2 is start from z0 to gamma through gamma 2 to point z1, and we say gamma is composition of is composition of gamma 1 and minus gamma 2. Here minus sign indicate that the if we go from z1 to z0 through gamma 1, and if we go from z1 to z0 for closed curve, then the direction of gamma 2 is different why we going. So we write here this minus gamma 2. So we can say that gamma is a composition of gamma 1 and gamma 2. Now we can say that here integral fz dz, fz dz is along gamma is equal to gamma 1 plus gamma 2. Here function is same, fz dz, fz dz. What we are given that integral of fz dz is equal to 0. So we put here right, on left hand side this value to 0. So we write 0 here, and gamma 1, this is a mistake. Here we also said gamma is composition of gamma 1 and minus gamma 2. So we write here minus gamma 2. So correct it, and we can write here gamma 1 fz, sorry, fz dz plus sign will be changed to minus due to we change the direction of moving from z0 to z1. If we change the direction, then um, uh, then this value is changed. Here we start from z0 to z. What if we write only gamma 2 in place of minus gamma? This means that we start from z0 to z. So we write here minus gamma 2 fz dz by the definition of definite integration, and correct is dz. We can now transfer this integral to left hand side. Then after transposition, the sign of this integral change minus to plus. So here we see that the integral is of a function is independent of curve, and it's only depend on the uh, first position and last position. So we can uh, say that this integral is independent of the path. So we can write a function. Let we define. Let us consider capital Fz. We define a function Fz is equal to a to z point. A is a fixed point on our domain D. Means this property, if we use this statement, then we can say that for this domain D, the starting point, the integral of fz is independent of curve, only depend on the starting point and final point. So this value is capital Fz according to this variable z, because a is fixed point. Therefore we can write f we will write here a initial point is fixed, and final point is some distance away from z. Here we say that z is written here, so z plus h will be right here. Here fz and f z plus h are two functions which is function of z. Because a is a fixed point in domain, we can write it here as this my same domain D of given domain, and point A is fixed point and Z this point, and H is a variable. What so we write here Z plus H, which is near to this. We take Z as a center and H mod is a radius and draw a circle. So we draw a circle which radius is mod H. We joined A to Z for this integral or this function f capital F Z. A, we choose any path from A to Z because we prove that this integral is independent of path. Also, we join in the same manner A to this point Z. Um, so we for this, and Z to Z plus H, we join this by straight line, and now we subtract equation 2 equation 1 from equation 2. We get on the left hand side by subtracting left hand side to left hand side z fz plus h minus fz is equal to a to z plus h fz dz minus a to z fz dz. Now we interchange the limit of second integral. So we write first as it, and interchange the lower and upper limit. But by this the sign of integral is changed, so this sign changed to minus to plus fz. And here we say that lower limit and upper limit of integrals are same and function are same also, also very well. So we use definition or property of definite integral, and common should be eliminated, and starting point z and final point z plus h, and common is function f z dz. So we write here f z plus h minus fz. In respect of figure, we can also draw previous curve here, z naught. I mean, both the graphs should be put in a single picture. So we write gamma 1 and gamma 2, and also therefore we can say that only this figure is sufficient for this MORERA theorem. Now we divide H both sides to prove that my MORERA theorem. For this dividing by H, whole equation divided by H is uh, difference between z and z plus h, and distance between these 2 points is modulus of h. So we write the previous equation as we can write here fz plus h minus fz whole upon h is equal to 1 upon h z2 z plus h ft dt. Here t dt in figure is the curve is for this integral is z to z plus h is a straight line from z to z plus h, and t is lie on a line on z to z plus h. So you understand what is t. T is a complex number lie on the line from starting point z to z plus h. Now we should go to next step, and we subtract our given function small fz. Here capital Fz is defined by us, and we subtract fz on the both side, from both side. So first we write previous entry, and now subtract equal thing, equal quantity fz both side. Now I work here on right hand side, that uh, we take 1 upon h outside, it means common from these, common outside. So z to z plus h fz dz, if we take 1 upon h from bracket, then we must multiply h here, because here is one, not 1 upon h available in this function fz factor, so we multiply h here, and we can write right hand side as z plus h minus z, because z that cancel out and only h is left, which is equal to given quantity. We can also write this quantity as this is value after putting the upper limit and lower limit. Variable here t, we can choose any variable to obtain our required result, so we choose t. In definite integral we can choose any variable, so we choose t for our requirement. This t variable, here we also see here, if we put the upper limit we get this value, and if we put lower limit we put that. So reverse process we can get this, and also we can get this value after integrating t with respect to t from z, from t is equal to z to z plus h, and fz is multiplied to this integral. What fz is independent of t, therefore we can say that fz is constant for t, so we can put this fz into this integral. So we multiply fz into 1, and we get this quantity. Here we say that the limit, lower limit and upper limit of integral is same, so we can take out z to z plus h. So we now obtain ft and minus fz here with respect to t. Now we take modulus both sides. What we should write here, complete the left hand side and right hand side. So we write left hand side fz plus h minus fz, and taking modulus both sides, we get here we write left hand side which is equal to right hand side. I put modulus to whole right hand side which is equal to left hand side. This is last steps of MORERA theorem. Now we apply this modulus to other parts, means factors. So left hand side, we will not write left hand side for sake of time, so only we write right hand side and put modulus on the h, and also put modulus on the functions ft minus fz, and also on dt. Now we know that f is continuous function which is given in statement of MORERA theorem in D. Fz is continuous in D for given epsilon greater than 0. I am writing the definition of, by the definition of the continuity, there exists a delta greater than 0 such that I apply the definition of function continuity, uh, continuous function, and definition of continuity, such that ft minus fz modulus is less than epsilon, where t minus z modulus is less than delta. We write this equation. If we put an equation, we write here equation 1 2, and now we write this as equation number 3, and this is equation number 4. Now since h is arbitrary h less than, so we put h modulus of h less than delta. This value in means t modulus of z minus t is less than delta, so I put h modulus of h less than delta, so that point t lying on the line, as VPDBS said, that line joining z to z plus h satisfies equation 4. This equation means we choose h such that modulus of s less than delta, so that all the points t lie on the line joining z to z plus h. Now we use equation number 3, and from equation number 3 we can write modulus of fz plus h minus fz over h minus fz is equal to 1 upon modulus of h dash and modulus of z to z plus h. I write here only equation number 4 here, repeat, and now apply the equation 4, and we use equation 4 here. So therefore 1 upon modulus h and z2 z plus h. This value is less than 2 epsilon by equation number 4. If we write in place of this, if we write epsilon in place of this, so the right hand side of value is greater than the left hand side. So we change this sign by inequality less than and write epsilon in place of this dt, modulus of dt. No change here. Now epsilon is a constant, so we should take epsilon out from integral and we get this value also dt. This value is greater than this value. What? This value equal to this value. So we use this sign, equal sign, and we should not confuse with these values are equal. This value is less and this value is greater. What this value are equal. So we use equal sign and here of integration of 1 with respect to t is t with limit z2 z plus h, and here we uh, put the upper and lower limit and we get z plus h minus z. Here we see that z is cancelled out, so there is problem here. Only del dt is modulus, so we apply dt here modulus, and also here t in modulus. Also uh, this step is wrong, so we should write a correct line. So we go to next step, right step. So apply upper limit by putting the value of t z plus h and minus lower limit by putting the value of t equal to z. So we write on the next page is equal to epsilon upon modulus of h, and here we write modulus z plus h minus mod of z. What we know that y inequality, y triangular inequality, modulus of a minus the modulus of b less than or equal to modulus of a minus b for real number of a and b. Also for complex number, because here are these two complex number, we can apply this theorem here, uh, which is equal to left hand side, yeah, or we can say that which left hand side is less than to this value. So because these two values are not equal, by applying this theorem we put this sign to connect this. Here we write epsilon and modulus of h as it and apply this theorem. So we apply modulus at whole, which is greater value than value separately modulus applied here. So z plus h minus z and z to z cancel out. Only uh, h modulus is left here, and I use equal sign which indicate only this value is equal to this, not left hand side equal to this. Left hand side is less than this value because we also um, uh, we previously this value is greater than left hand side, and also this value also greater than this, this value is also greater than this value. This value is also greater than this value. This value is greater, therefore left hand side is less value. So if we write left hand side, then we we will use sign of inequality. Here we say that this sign is cancel out, mod of h cancel out. Therefore, now applying limit h tends to 0 means z and z plus h point is very near to each other. So we apply this limit and we get our required result. Here only equal this value equal to epsilon, and left hand side we can write epsilon. This value is left hand side value is less than epsilon, or also we apply here limit h tends to 0. If h tends to 0, then epsilon tends to 0 as s tends to 0. What this value is a positive value, so this value is not negative. What was less than epsilon, epsilon also tends to 0, so this value is equal to 0. So we put capital Fz plus h minus fz upon h, where we know that limit h tends to 0 minus fz equal to 0. This is definition of uh, differentiation of fz, derivative of fz. So we it's right in this one, and if a modular of complex number is 0, then this that complex number is 0. So we write this as, and also f dash z equal to fz, and we say now fz, since fz means this function, given function and defined function, fz exists, this function exists, so which is equal to f dash z is so f dash is also exist. Therefore we can say that f dash z exists, so fz is without here without derivative, fz is differentiable, because differentiable is exists. Therefore we can say fz is differentiable function in z belong to D. Therefore we can say that capital Fz is analytic in D. Consequently, f dash z rest small fz is also analytic in D, because derivative by theorem we can say that by other theorem we can say that because the derivative of an analytic function, because derivative of an analytic function is also analytic. This last statement is said by a theorem which is not proved here, but we can use for proof of MORERA theorem, which is our result, because fz is analytic function. Thank you very much indeed for listening me.